Hello and welcome to the first video of Introduction to Digital Logic. In this video I'm going to introduce to you the 6 most important digital logic gates. Now there are others, but these are the 6 most important, and I'm going to try to talk to you a little bit about each of them in turn. A logic gate is really just simply a device that accepts one or more binary inputs, or we can refer to them as digital inputs if we're talking about the circuit. So it receives one or more digital or binary inputs and delivers one or more outputs based on a rule that combines the input in a structured manner. So it will yield the same sort of behavior every single time that you send inputs into the circuit. Now there are many of these, but we're going to consider 6. There's the AND, the OR, the NOT, the NAND, the NOR, and the XOR. Of these, the AND, the OR, and the NOT are the most important, so we're going to spend most of the time on those. Here you can see the symbol for an AND gate. An AND gate, be careful when you're drawing it. Remember that the back, the left-hand side, the input side of an AND gate is supposed to be straight. It's supposed to be vertical and no curve. And then the output side, the right-hand side, is supposed to be curved. And so it's just curved, continuously smooth, sort of like a half circle. The symbol for an AND is going to be this dot. It's just the same exact dot that we would use for multiplication in regular algebra, and we'll see that there is some analogy between the AND operation and the multiplication operation. But if you see this, you don't say A dot B, you say A and B. You don't say A times B, it's A and B. Now what's the behavior of the AND gate? The AND gate will output a 1 if and only if both of the inputs are a 1. So here you can see this is known as a truth table. And in this truth table, I've listed every possible combination of the 2 inputs. There's 0, 0, there's 0, 1, there's 1, 0, there's 1, 1. I 100% guarantee you that those are the only 4 possible combinations of 2 inputs. And so you can see here, the 0, 0, well, that will yield a 0 for sure, because the AND gate is looking for both inputs to be a 1. And in this case, neither input is a 1, so it's definitely going to be a 0. In the next 2 rows, well, you're halfway there, but in both cases, we still need the other input to be a 1. And so both of these, the output is going to be a 0 as well. Only in the last row do we see that the output actually becomes a 1. So that's the symbol and the truth table for an AND gate. Now an AND gate accepts 2 inputs, although it could accept 3 or 4 or more inputs. I've seen AND gates with as many as 8 inputs. And in any case, only if all of the inputs are 1, only then does the output equal 1. Here you can see the truth table for an OR gate as well as the symbol for an OR gate. Notice that on the OR gate, the back edge or the input edge is curved and the output edge is pointed. And so when it's sort of a rookie mistake when working with these digital logic gates to draw your AND gates and your OR gates so that they kind of get a little bit confusing. Make a definite curve on the backside and a definite point on the output for the OR gate, and then just to distinguish it, on the AND gate, a straight edge on the backside and then a curve, a nice smooth continuous curve on the output. You'll be much better off, and that way you won't ever get them confused. The equation would say A plus B if this were regular algebra, but of course it's Boolean algebra, so this is A or B. And so we would say A or B. If we see this expression, we'll say A or B. What does the truth table look like? Well, here's that same 4 combinations of the 2 inputs, but for an OR gate, as the name suggests, if either or both of the inputs are 1, then the output will also be a 1. The only way that an output of an OR gate can be 0 is if both of the inputs are both 0. And so that's the logic, that's the characteristic of an OR gate. For an inverter, which is also known as a NOT gate. So you either have a NOT gate or it's also known as an inverter. To represent this, we're going to put a bar over the variable. And the output of the inverter is just simply going to be the opposite of the input. So this only has 1 input. If it's a 0, it becomes a 1. If it's a 1, it becomes a 0. That's really all that there is to an inverter. This is usually referred to as not A, although sometimes we will also refer to it as A bar. Either of those is fine. They're really completely equivalent to each other. And one good thing to remember, to think about, is that in this case, I always think of the circle on the end as actually doing the inversion. I kind of think of the triangle as just sort of drawing attention to the fact that there's a circle there so you don't accidentally miss it. If you think of this, and by the way, we call this circle a bubble. It's just what it's always been called, so that's what we continue to call it. If you think of that circle as the thing that actually does the inversion, that will really come in handy for the next 2 gates that we're going to consider. The next gate is a NAND gate. Now, NAND is a contraction of not AND. And so essentially what you can see here is that this is like an AND gate. It's exactly the same shape as an AND gate, but it has that same bubble from the inverter. And so what that means is that first of all, you AND together A and B, and then you put a bar across the whole thing. So that means you do an AND operation followed by an inversion. Remember that for the AND, only the last row was a 1. All the others were 0. And so we've just flipped every one of those bits. Now only the last row is a 0, all the others are a 1. And so that's what the output of a NAND gate looks like. You might be saying to yourself right now, why in the world would you bother to have a separate gate that could be implemented by 2 existing gates? And the answer is, there is a good answer. The answer is beyond the scope of today's lesson, but I promise you're going to learn about it soon. NAND gates and the next gate we're going to see, the NOR gate, are very special, and they're very special for a very important reason. So here's the NOR gate. I sort of mentioned that a second ago. This is an OR gate followed by an inverter. So you can see it's A or B with a bar across the whole thing. Remember before it was 0, 1, 1, 1 for an OR gate, and now for a NOR gate, it's 1, 0, 0, 0. So A NOR B will only be 1 if both of the inputs are 0. And then finally, the last gate is an XOR gate. So it's pronounced XOR, and you can see here, this is, it's also short for exclusive OR. So this is exclusive OR. What this says is, and by the way, here's the symbol, is that it's just like an OR gate, except it has the second copy of the back edge curve there. And the algebraic symbol is to have a plus sign with a circle around it. So it's just like OR, but a little bit different. So the circle signifies the similarity to OR. Now remember that in OR it was 0, 1, 1, 1. If either of the inputs or both of the inputs are 1, then the output will also be a 1. Well, in the case of XOR, the only difference is in the last row. And that's because if both of the inputs are 1, then the output actually reverts back to a 0. The way that I like to think of it is that this is detecting if the 2 inputs are the opposite. So 0, 1 gives a 1. 1, 0 gives a 1. But if the 2 inputs are the same, 0, 0 gives a 0, 1, 1 gives a 0. And at this point, you might say, well, that doesn't seem very helpful. Why would you need that? I'll just mention that exclusive OR gates are extremely useful when it comes to doing arithmetic, especially addition, subtraction, multiplication, and division. And so if we get into those sorts of circuits in this class, or if you see them next year, you'll certainly make very good use of an exclusive OR gate. Okay, so those are the 6 fundamental gates. I just wanted to mention that you can, of course, expand the gates to have more than 2 inputs. And so here you can see the truth table. Here's a truth table with 3 variables as the inputs. So there's 8 rows. 2 to the 3rd is 8. So there are 8 different combinations. Again, I swear to you, these are the only possible 8 combinations of those 3 inputs. And here you can see that since this is an AND gate, only if all 3 of the inputs are 1, only then does the output equal a 1. And the same thing is true for the OR gate, the NAND gate, the NOR gate. You need to understand the fundamental behavior of the gate, and then it's very easy to understand how it would expand out to more than 2 inputs. Okay, time to work on the digital logic gates example problem. Go ahead and try that on your own, then watch the video, and then come back and we'll talk a little bit about perfect induction.